In the summer of 1921, a man walked into the Bureau of Ordnance of the United States Navy carrying a reputation for brilliance and a personality that his colleagues described with remarkable consistency as impossible. His name was Carl Lucas Norden. He had been born in 1880 in Semarang, Java, the son of a merchant who died when the boy was 5. He had been shipped to boarding school in the Netherlands, then to Dresden, then to the Federal Polytechnic Institute in Zurich, where he studied mechanical engineering alongside a fellow student named Vladimir Lenin, another man of iron discipline and limitless stubbornness, though with different ambitions. Norden emigrated to America in 1904 with a degree, an accent, and an absolute certainty that he was the finest mechanical engineer alive. He may have been right. For 4 years, he had worked at the Sperry Gyroscope Company on Long Island, helping design the gyro stabilizers that kept warships from rolling in heavy seas. The work was brilliant. The working relationship was not. Norden clashed with Elmer Sperry over salary, over credit, over everything that two proud men with large egos and small patience can fight about. Norden demanded a $25 weekly raise. Sperry refused. Norden quit. The two men would feud for decades, each claiming the other had stolen his ideas, each convinced the other was a fraud. Norden went out on his own, taking with him an expertise in gyroscopic stabilization that no one else in America could match, and a temperament that the Navy's engineers would learn to call Old Man Dynamite. The Navy did not come to Norden because they liked him. They came because they had a problem that no one else could solve. Bombs dropped from airplanes missed their targets. They missed by hundreds of feet, by thousands. In the First World War, bombardiers had aimed by leaning over the side of the cockpit with a stopwatch and a prayer. The results were indistinguishable from random chance. The Navy wanted a device, a mechanical instrument of such precision that a bombardier could put a bomb on a target from 20,000 feet, a height at which the target was invisible to the naked eye. They wanted a machine that could do the mathematics of falling objects in real time, while the aircraft pitched and rolled and yawed through turbulent air, while the wind blew the bomb sideways, while the Earth's gravity pulled it down along a parabolic curve that shifted with every fluctuation of airspeed and altitude. They wanted the impossible. They came to the one man arrogant enough to believe he could build it. The physics of bombing is simple to state and murderously difficult to solve. A bomb released from an airplane does not fall straight down. It carries forward at the speed of the aircraft. Simultaneously, gravity accelerates it toward the ground. The wind pushes it sideways. Air resistance slows its forward motion and creates drag that varies with altitude and temperature. The result is a curved trajectory, a parabola modified by aerodynamic forces that deposits the bomb at a point on the ground that is not directly below the aircraft at the moment of release, but far ahead of it, displaced by wind, altered by the air the bomb falls through. From 20,000 feet, the bomb falls for approximately 30 seconds. During that time, the aircraft moves forward nearly 2 miles. The bomb must be released 2.5 miles before the aircraft reaches the target. At the moment of release, the bombardier cannot see the point of impact. He is aiming at a mathematical abstraction, a point in space and time that the bomb and the ground will occupy simultaneously, half a minute in the future. To calculate that point, the bombardier needs to know the aircraft's altitude precisely, its true airspeed, the speed and direction of the wind at every altitude the bomb will pass through, the ballistic characteristics of the specific bomb type, and the aircraft's exact heading. He needs to integrate these variables continuously as the aircraft approaches the target, because the wind changes, the airspeed fluctuates, and the heading drifts. He needs to solve this problem in the last 60 seconds before the drop, while wearing an oxygen mask at a temperature of 40 degrees below zero, while anti-aircraft shells burst around the aircraft, while fighters attack, while his own gunners fire, and the bomber shudders from recoil and turbulence and the concussion of near-miss flak. No human being can do this calculation. The mathematics are not difficult. A first-year physics student can solve the equations on paper. but solving them in real time, continuously, while the variables change every second, while the world explodes around you. That requires a machine. In the 1920s and early 1930s, the bomb sights available to the American military were essentially mechanical slide rules. The bombardier dialed in altitude, airspeed, and wind direction. The sight calculated a fixed dropping angle. When the target passed through the crosshairs, the bombardier pressed a button and the bombs fell. These sights worked reasonably well against stationary targets in calm air from moderate altitudes. They were useless against moving ships. They were dangerously inaccurate in wind. And they could not account for changes in flight conditions during the bomb run because they calculated a single answer and held it, like a photograph of a river, accurate for one instant, obsolete the next. What was needed was not a calculator, but a computer, a device that solved the bombing equations not once, but continuously, updating the answer every fraction of a second as conditions changed, a machine that could think faster than the wind. Norden spent 6 years building it. He worked from his home, from his partner Theodore Barth's apartment, from the workshops of the Whitman Lewis Aircraft Company. He employed no assembly line. He had no factory. Every prototype was handmade, every gear cut to his specifications, every bearing polished to a tolerance that watchmakers would have considered excessive. Barth was his perfect counterpart, a practical engineer and former Army colonel who had managed gas mask production during the First World War. Barth was charming where Norden was abrasive, diplomatic where Norden was contemptuous, businesslike where Norden was obsessed. The Navy had recommended the partnership specifically to free Norden for design work, and it succeeded. Barth handled contracts, negotiations, and the task of preventing Norden from insulting every government official who walked through the door. Together, they incorporated Carl L. Norden Incorporated in 1928. The company would eventually produce one of the most consequential weapons of the Second World War. But in the beginning, it was essentially one Dutchman's workshop, filled with the smell of machine oil and the sound of spinning gyroscopes. The device Norden created, designated the Mark 15 by the Navy, the M series by the Army, was a masterpiece of mechanical engineering and a nightmare of mechanical complexity. It consisted of 2 primary sections. The stabilizer, mounted below, contained a directional gyroscope spinning at 7,200 revolutions per minute. This gyroscope provided an inertially stable platform, a reference point that did not move even when the aircraft pitched, rolled, and yawed. It was the fixed point in a moving universe, the artificial horizon against which everything else was measured. Above the stabilizer sat the sight head, containing the analog computer, the sighting telescope, and the bombardier's controls. The computer was not electronic. It was entirely mechanical, an intricate assembly of more than 2,000 parts, gears, cams, differentials, clutches, levers, potentiometers, mirrors, and direct current motors whose carbon brushes shed a fine black dust into the precision bearings they were supposed to serve. Norden despised alternating current the way some men despise weakness. He insisted on DC motors throughout the device, a decision that introduced maintenance problems he stubbornly refused to acknowledge. The Bombsight worked on a principle that was elegant in theory and agonizing in practice. The bombardier looked through a low-powered telescope mounted on a rotating prism. A motor inside the computer turned the prism at a rate calculated to cancel out the apparent motion of the ground below. If the motor speed was correctly set, the target appeared stationary in the telescope's field of view, frozen in place while the Earth slid past beneath it. The bombardier's task was to adjust the controls until the target truly stopped moving. When it did, the bombsight knew the aircraft's ground speed and drift angle. From these inputs, combined with altitude and bomb type, the computer continuously calculated the dropping angle, the precise moment when the bombs should release. The device was connected to an autopilot that allowed the bombardier, not the pilot, to fly the aircraft during the final moments of the bomb run. The autopilot's servo motors could execute 5 reversals per second, making corrections smoother and faster than any human hand on the controls. During those final seconds, the bombardier was effectively flying the airplane through the bomb site itself, guiding a 40-ton bomber onto a mathematical point in space with the delicacy of a watchmaker adjusting a mainspring. The first production bomb sight was delivered in 1931. In controlled testing, it demonstrated a circular error probable of 75 feet from altitude. This was astonishing. This was revolutionary. This was the foundation on which the entire American doctrine of strategic air warfare would be built. The legend grew fast. The Norden Company, with Barth's talent for promotion and Norden's willingness to believe his own machine was infallible, cultivated a reputation that became one of the great myths of the war. Bombardiers, they claimed, could put a bomb into a pickle barrel from 20,000 feet. The press loved it. The public loved it. The Army Air Corps loved it because the pickle barrel promise justified everything they wanted, a strategic bombing doctrine that could win wars without the horror of trench warfare, without the need for massive ground invasions, without the terrible human cost of sending infantry into machine gun fire. If you could destroy a nation's factories, its rail yards, its power plants, its ball-bearing works from the stratosphere, you could cripple its ability to fight without ever setting foot on its soil. The reality was less inspiring. A pickle barrel from 20,000 feet would be completely invisible through the Norden's 20-power telescope. It would be smaller than the crosshairs themselves. In training, the average Army Air Corps bombardier achieved a circular error of 400 feet from 15,000 feet. Not 75 feet, not a pickle barrel, 400 feet, under ideal conditions, with no wind, no flak, no fighters, no oxygen masks, no frozen fingers, no terror. But the myth served a purpose. It gave the bombardiers a sense of pride and precision. It gave the American public confidence that their sons were not dropping bombs randomly on cities, but placing them with surgical accuracy on military targets. And it gave the Army Air Forces the political cover to pursue a strategy of daylight precision bombing that would consume enormous resources, cost staggering numbers of lives, and produce results that were, for most of the war, deeply disappointing. The security surrounding the Norden Bombsight was, for a military instrument, unprecedented. It was classified at a level that rivaled the Manhattan Project. The factory that produced it was unnamed in public records. No photograph of the device was released until 1944. The plant required 350 armed guards at all times. 2 personal bodyguards accompanied Carl Norden wherever he went. Bombardier trainees were required to swear a solemn oath, the Bombardier's Oath, pledging to protect the secret of the Norden with their lives if necessary. They were trained to destroy the device if their aircraft was forced down in enemy territory. The initial procedure was to shoot the most critical components with a pistol. Later, thermite incendiary devices were installed that could melt the bomb sight into a pool of unrecognizable metal in seconds. Before every mission, the sight head, the upper portion containing the computer, was removed from the aircraft and stored in a climate-controlled, dust-proof bomb vault patrolled by armed guards. When it was time to fly, an ordnance technician carried the sight head to the aircraft in a canvas bag, escorted by 2 guards armed with Thompson submachine guns. The bombardier installed it in the nose of the bomber and was under orders not to remove the cover until the aircraft was airborne. This extraordinary secrecy was, in one of the war's great ironies, entirely pointless. A German spy named Hermann Lang, employed at the Norden factory on Lafayette Street in Manhattan, had stolen the complete plans in 1938. He reconstructed them from memory during a visit to Germany and delivered them to the Abwehr, German military intelligence. Lang was eventually arrested in 1941 as part of the Duquesne spy ring, the largest espionage prosecution in American history, and sentenced to 18 years in prison. But the damage was done. German engineers studied the blueprints, built a working replica, and reached a conclusion that said as much about German strategic thinking as it did about the bomb sight itself. They declared it too complicated to manufacture, too difficult to operate, and no better than their own Lot-Fernrohr 7. They were right about the complexity. They were wrong about the implications. Before the war, production of the Norden Bombsight was glacial. Carl L. Norden Incorporated, operating from its small factory in Manhattan, produced just over 100 bomb sights per year. Each one was essentially a handmade precision instrument. The 2,000 parts required machining to tolerances that were, at the time, unheard of in mass production. The 61 ball bearings inside each unit were in such short supply that Norden and Barth established a separate company, the Barden Corporation, from Barth and Norden, specifically to manufacture them. Norden trained the workers himself. He trusted no one else to teach them. When war came, the demand was catastrophic. The Army Air Forces alone needed tens of thousands of bomb sights for their expanding fleet of B-17s, B-24s, B-25s, and eventually B-29s. The tiny Manhattan factory could not come close. The Navy signed a contract with Lucas Herald Corporation, a wholly owned subsidiary of Carl L. Norden, Inc., to build and operate a government-owned, contractor-operated facility in Indianapolis. The Indianapolis Naval Ordnance Plant was commissioned in May 1942 and immediately began producing bomb sights and gunnery fire control instruments. Of the 12,792 bomb sights produced at Indianapolis, over 11,000 went to the Army Air Forces. But even Indianapolis was not enough. The government turned to companies whose expertise in precision mechanical assembly matched the bomb sight's demands. The Victor Adding Machine Company, a manufacturer of mechanical calculators whose workers were accustomed to assembling intricate gear trains and registering mechanisms, became a major Norden producer. The bomb sight that Tom Farabee used to drop Little Boy on Hiroshima, serial number Victor 4120, was manufactured by Victor. The same company that built machines for accounting offices built the device that aimed the first atomic bomb. Remington Rand, another business machine manufacturer, joined the production effort. By 1943, factories across the country were producing Norden components. The scale was enormous. By the end of the war, nearly 90,000 complete bomb sights had been manufactured at a total program cost of $1.1 billion, half the cost of the Manhattan Project, a sum that would equal approximately $17 billion today. Each bomb sight cost roughly $8,800 for the sight head and $4,200 for the stabilizer, $13,000 per unit in an era when a new automobile cost less than $1,000. 50,000 bombardiers were trained to operate them. The Norden Bombsight was, by any measure, one of the most expensive weapon systems of the entire war. To understand what the Norden demanded, you have to understand the man who operated it. The bombardier sat in the nose of the aircraft, in a plexiglass greenhouse that offered a magnificent view of the approaching landscape and absolutely no protection from anything. He was the most forward human being in the aircraft. Everything in front of him was glass. Beneath him was air, and beneath the air was a country that wanted to kill him. He wore a fleece-lined leather jacket, a Mae West life preserver, and a parachute harness. At 25,000 feet, the temperature outside the glass was 40 degrees below zero. The heating system in the nose of a B-17 was unreliable at best. Many bombardiers flew with electrically heated suits that shorted out, with gloves so thick they could barely grip the tiny adjustment knobs on the Norden, with oxygen masks that leaked and fogged their goggles and sometimes froze to the skin of their faces, tearing it when removed. Before the mission, the bombardier retrieved the sight head from the bomb vault, a guarded, climate-controlled bunker on the airfield. He signed for it, as a man signs for a diamond from a bank vault. He carried it to the aircraft in a canvas bag, flanked by 2 armed guards. He installed it on the stabilizer, which remained permanently mounted in the nose. He connected the electrical cables, the autopilot linkage, the bomb release mechanism. He leveled the gyroscopes, a process that could take 8.5 minutes, requiring him to peer through a small window at 2 bubble levels and make tiny adjustments until both bubbles centered. If turbulence tumbled the gyro during the approach, he had to start the leveling process again, losing minutes he did not have. During the bomb run, typically the last 60 to 90 seconds before release, the bombardier took control of the aircraft through the autopilot connection. He called over the intercom, "I've got it." The pilot released the controls. For the next minute, the most lethal aircraft in the formation was being flown not by the man with the flight training and the view of the sky, but by the man staring through a 20-power telescope at a patch of ground that was growing slowly closer. The bombardier made his adjustments. He dialed in the crosswind. He tracked the target, keeping it centered in his field of view, adjusting the rate knob until the target appeared absolutely stationary. He watched the indices on the side of the sight head, 2 pointers sliding toward each other on a scale. When they met, the bombs released automatically. He did not press a button. The machine decided when the geometry was correct. The machine decided when to drop. In the seconds before release, the aircraft flew straight and level. No evasive maneuvers, no banking, no turning. The flak gunners on the ground knew exactly what a bomber on its bomb run looked like, steady, predictable, holding course with mechanical precision. The final minute of the bomb run was the most dangerous minute of the entire mission. The aircraft was a target, flying in a straight line, at a constant altitude, at a predictable speed, while every anti-aircraft gun in the area poured fire into the sky around it. The men who flew those last 60 seconds, bombardiers with names now forgotten, boys of 20 and 21 who had trained on adding machines converted into bombsights, who had sworn an oath to die for a device they barely understood, were among the bravest men of the war. And most of them missed. And then the Norden went to war, and the war broke it. Not physically, though the Nordens broke physically too, constantly, maddeningly, their DC notors shedding carbon dust into bearings that seized, their gyroscopes tumbling in turbulence and requiring 8.5 minutes of painstaking re-leveling, their mechanical integrators drifting, their precision components shaken loose by the vibration of 4 engines and the concussion of anti-aircraft fire. The real failure was the gap between the pickle barrel and reality. In combat over Europe in 1943, the average circular error probable was 1,200 feet, not 75. Only 50% of American bombs fell within a quarter mile of the target. 90% missed entirely by the most generous standards of accuracy. The average bombardier, hunched over his telescope at 25,000 feet, breathing pure oxygen through a rubber mask that froze to his face, wearing gloves that made the tiny adjustment knobs nearly impossible to grip, could not achieve anything close to the accuracy the doctrine demanded. The reasons were numerous and unforgiving. Cloud cover over Europe was endemic. Targets were obscured on the majority of mission days. Smoke from fires started by previous raids blanketed industrial areas. Anti-aircraft fire forced evasive maneuvers that disrupted the bomb run. Fighter attacks broke formations. The jet stream at high altitudes scattered bombs across miles of landscape. The bombardier had to consult ballistic tables and perform calculations on a handheld slide rule while his aircraft was being shot at, then peer through a 20-power telescope at a target that was frequently invisible. The British, who had already abandoned precision bombing in favor of nighttime area raids, watched the American obsession with the Norden with a mixture of respect and pity. They had tried daylight precision bombing and concluded it was suicidal. They told the Americans so. The Americans persisted, driven by a doctrine that demanded precision and a bombsight that promised it. And yet, it worked often enough to matter, often enough to justify the doctrine, the expense, the lives. On March 18, 1943, the 303rd Bombardment Group attacked the submarine construction yards at Bremen-Wegesack, Germany. 76% of their bombs fell within a 1,000-foot ring of the target. It was the first large-scale demonstration that the Norden, in the right hands, under the right conditions, could deliver concentrated destructive power on a specific industrial facility from altitude. The submarine pens were damaged. The message was received by the Germans, by the British, and by the American planners who had staked everything on the doctrine of precision. The Schweinfurt raids of 1943 targeted the German ball bearing industry, an irony that would have pleased Carl Norden, whose own bearings had been the most difficult component to manufacture. The attacks were designed to cripple Germany's ability to produce the precision components that every tank, every aircraft, every submarine engine required. The raids caused significant damage to the factories, though at a cost in aircraft and crews that was nearly unsustainable. 60 bombers were lost on the second Schweinfurt raid alone, 600 men killed, wounded, or captured in a single afternoon. That is 60 Norden Bombsights that were supposed to be destroyed by their bombardiers before the aircraft hit the ground. Many were. Some were not. Some bombardiers were already dead when their aircraft went down, killed by flak or cannon fire that punched through the plexiglass greenhouse where they sat, fully exposed, staring through a telescope at a target that was trying to kill them. The Germans examined captured Nordens with professional curiosity and confirmed what their engineers had already concluded from the stolen plans. It was an impressive machine that would not change their own approach to bombing. Later in the war, tactics improved. The lead bombardier system was adopted. In a formation of 36 aircraft, only the lead bombardier used the Norden to aim. When his bombs released, every other bombardier in the formation dropped on his signal. This multiplied the effectiveness of a single good bombardier across the entire formation and reduced the impact of the many who were average or poorly trained. The lead bombardier became the most critical crew member in the entire formation, one man with one bomb sight responsible for the accuracy of every bomb dropped by every aircraft flying behind him. The introduction of H-2X radar, Mickey, to the crews allowed bombing through cloud cover by providing a crude radar image of the ground. The H-2X worked best near coastlines where the contrast between water and land produced a distinctive return. It was married to the Norden, the two systems working in tandem, the radar to find the target area, the bomb sight to refine the aim. It was not precision. It was better than blindness. In the Pacific, the Norden faced different challenges entirely. The B-29s attacking Japan from bases in the Mariana Islands flew at altitudes above 30,000 feet, where the jet stream pushed winds to velocities exceeding 200 miles per hour. The Norden had not been designed for such conditions. Its mechanical integrators could not keep pace with wind corrections of that magnitude. Bombs dropped from that altitude in that wind scattered across miles of landscape. The circular error widened to distances that made precision bombing meaningless against anything smaller than an entire urban district. General Curtis LeMay, commanding the B-29 force, studied the results and made a decision that overturned everything the Norden represented. He abandoned high-altitude daylight precision bombing entirely and switched to low-altitude nighttime incendiary raids. The bombers would fly between 5,000 and 9,000 feet. They would fly at night when Japanese fighters could not find them. They would carry incendiary bombs designed to set fire to the wooden cities of Japan. They would not need precision. They would need only volume. The Norden, the most expensive bomb sight in history, was effectively set aside. Some aircraft carried simpler sighting equipment for the low-altitude runs. The billion-dollar investment in precision was replaced by a doctrine of area destruction that made the pickle barrel promise seem like a cruel joke. The Tokyo firebombing raid of March 9–10, 1945 killed an estimated 100,000 people and destroyed 16 square miles of the city. It was the most destructive air raid in human history. The Norden Bombsight played no significant role. But when the atomic bombs were dropped, the Norden was there. Tom Farabee, the bombardier of the Enola Gay, used Victor 4120, a Norden M9B manufactured by the Victor Adding Machine Company, to aim Little Boy over Hiroshima on August 6, 1945. The bomb missed its aiming point, the Iowa Bridge, by approximately 800 feet. Under any other circumstances, this would have been an unacceptable error. With a nuclear weapon, it was irrelevant. The Norden had spent $1 billion perfecting accuracy for a weapon that did not require it. The German Lot-Fernrohr 7, built by Carl Zeiss, a company whose name was synonymous with optical perfection, was a competent bomb sight that shared many principles with the Norden. It used gyroscopic stabilization, it used a synchronous sighting mechanism, it connected to an autopilot. In some respects, it was simpler and more practical than the Norden, easier to manufacture and easier to maintain. But the Germans never built a strategic bombing force. They never invested in four-engine heavy bombers capable of sustained operations over long distances at high altitudes. Their doctrine emphasized tactical air support, close cooperation with ground forces, dive bombing, and medium-altitude attacks. For this kind of warfare, the Lot-F 7 was adequate. The Norden's advantage, its ability to perform continuously updated calculations for high-altitude, long-range bombing, was irrelevant to a nation that did not bomb from 30,000 feet. The Japanese captured intact Norden Bombsights from downed B-25s and developed a simplified copy, the Type 4 automatic bombing sight. They found it too complex to mass produce. Their manufacturing base could not achieve the tolerances that American manufacturing bases, adding machine companies, business machine manufacturers, precision instrument makers, delivered by the tens of thousands. This was the asymmetry that mattered. Not the bomb sight itself, but the industrial culture that produced it. America could take a 2,000-part mechanical computer designed by a perfectionist who refused to compromise on a single bearing and hand it to the Victor Adding Machine Company and say, "Build 90,000 of these and build them now." And Victor could do it, because their workers already knew how to assemble intricate gear trains, because their factories already had the precision tooling, because the American manufacturing base, forged in the mass production of typewriters and adding machines and cash registers and clocks, possessed a depth of mechanical precision that no other nation on Earth could match at scale. The Norden Bombsight served in Korea, where its mechanical computers struggled against targets approached at jet-age speeds. It was still in service during Vietnam, when Navy Squadron VO-67 used it in 1967 to drop acoustic sensors along the Ho Chi Minh Trail, its last combat mission, a quarter-century after it was designed. After the war, surplus Nordens flooded the market. The device that had been guarded by armed men with Thompson submachine guns that bombardiers had sworn to defend with their lives was eventually sold by mail-order houses for $24.50. The gyroscopes were cannibalized by hobbyists. The precision gears became novelties. The instrument that had cost $13,000 and a solemn oath became a conversation piece mounted on a plow disc in a veteran's living room. Carl Norden returned to Switzerland, where he died in Zurich in 1965. He never stopped believing that his bomb sight could hit a pickle barrel from 20,000 feet. The evidence suggests he was wrong, but the evidence also suggests that he was asking the right question, the question that would eventually be answered not by mechanical computers and gyroscopes, but by lasers and GPS satellites and silicone chips. How do you put a weapon precisely where it needs to go? The Barden Corporation, the ball bearing company that Norden and Barth created to solve their most critical manufacturing problem, still exists today. In one of history's more pointed ironies, it is now part of the German FAG Bearing Group, headquartered in Schweinfurt, the very city whose ball bearing factories the Norden Bombsight was used to attack in the bloodiest raids of 1943. The instrument designed to destroy Schweinfurt's bearings needed Schweinfurt's bearings to exist. The Norden Bombsight was simultaneously one of the most brilliant and most disappointing weapons of the Second World War. It was brilliant because it attempted to solve a problem that was mathematically unsolvable by human means in real time: the continuous calculation of a bomb's trajectory through a changing atmosphere from a moving, unstable platform. It was disappointing because it could never fully deliver on the promise that justified its existence, the promise that strategic bombing could be precise enough to destroy military targets without destroying everything around them. But the legacy is not in the accuracy. The legacy is in the ambition. The Norden Bombsight represents the moment when warfare crossed from human skill to machine calculation. Every guided weapon that exists today, every laser-guided bomb, every GPS-directed munition, every cruise missile that flies through a window is a descendant of the mechanical analog computer that Carl Norden built in a Manhattan workshop, the device that a Dutch immigrant with an impossible temperament assembled from gears and gyroscopes and the stubborn conviction that precision was a moral imperative. Norden himself believed this. He was a devout Christian who insisted he was a designer, not an inventor, because only God could invent. He believed the bombsight would make war more humane, that precise bombing would spare civilians, shorten wars, and reduce suffering. The firebombing of Tokyo, the atomic destruction of Hiroshima and Nagasaki, the very missions that used his bombsight proved him catastrophically wrong. But his intention was real. He wanted to build a device so accurate that war would become surgical rather than savage. 90,000 bombsights, 50,000 trained bombardiers, $1.1 billion, a Latin motto about pickle barrels, an oath sworn on a Bible to destroy the machine rather than let it be captured. 2,000 intricately machined parts inside a 50-pound analog computer, each part manufactured by workers from adding machine companies and precision instrument shops and ball bearing factories, workers who brought to the weapons of war the same meticulous craftsmanship they had applied to cash registers and calculating machines and the tiny gears inside a woman's wristwatch. Today, if you visit the Smithsonian's National Air and Space Museum at Dulles Airport in Virginia, you can see the Enola Gay suspended from the ceiling of the Udvar-Hazy Center. If you look into the plexiglass nose, you can see the Norden Bombsight, Victor 4120, still mounted in position. The device that aimed the first atomic bomb is a few feet away from the visitor, behind glass, silent, its gyroscopes still, its gears locked, its computer forever solved. It looks small. That is the first thing you notice. This 50-pound collection of metal and glass and mechanical ingenuity, this device that cost $1 billion to develop and produce, that was guarded by armed men, that bombardiers swore to destroy with their lives, that was carried to the aircraft under escort like a prisoner or a crown jewel. It looks like something you might find in a watchmaker's workshop. Intricate, delicate, beautiful in the way that precision machinery is always beautiful, and entirely, heartbreakingly obsolete. Every guided weapon that exists today, every laser-guided bomb, every GPS-directed munition, every cruise missile that flies through a specific window of a specific building is a descendant of the mechanical analog computer that Carl Norden built in a Manhattan workshop. The question he asked, how do you put a weapon precisely where it needs to go, is the question that drives every weapons program in the world today. He answered it with gears. We answer it with satellites. But it is the same question, asked first by a Dutch immigrant with an impossible temperament, assembled from 2,000 parts by workers from adding machine companies, carried to war in a canvas bag by boys who swore an oath to protect it with their lives. 90,000 bombsights, 50,000 trained bombardiers, $1.1 billion, a motto about pickle barrels, an oath sworn on the Bible, a spy who stole the plans for $1,500, a ball-bearing company named after its founders that ended up owned by the very Germans whose ball-bearing factories the bombsight was designed to destroy. That is the story of the Norden Bombsight. Not a story of perfection, a story of ambition so enormous that it reshaped an entire industry, justified an entire doctrine of warfare, consumed $1 billion of a nation's treasure, and still, in the end, could not make a bomb hit a pickle barrel from 4 miles in the sky. But it tried. And in the trying, it asked the question that would define the next 80 years of warfare. Can a machine aim better than a man? The answer, which Carl Norden pursued with the fervor of a prophet and the precision of a watchmaker, turned out to be yes, just not his machine. Not yet. Not with gears and gyroscopes and DC motors shedding carbon dust into bearings that seized in the cold. The answer would come later, with electronics he despised and technology he could not have imagined. But the question was his, and the question was everything.